So very often, I think inventions are made not necessarily in a linear fashion, right? It's not we're going to fund this research, we're not going to fund the research, invent something, right? Because invention or discovery very often is unexpected. So what I think is that several components are key as we reflect back to see what led to this, right? In fact, really our engagement, we have been engaged with the BMW for a large number of years. I think they supported us over maybe 7 or 8 years with very large amount of funding. To them, to my understanding, what they convey to us, the investment with my group is the largest ever in terms of sponsorship for BMW as a whole, as a company. Right? For any academic startup, that's maybe a different story. So that they had study funding and they challenge, they are not necessarily asking us to make incremental improvement. They give us questions. We need to be able to predict life for lithium-ion batteries for 10 years, but we have no idea what's happening on the electrolyte interface. We have learned from our, they have plenty of suppliers telling them all various possible solutions, and there's various quick fixes or solutions, adding additives and this and that, and that can enhance the performance. But they really realize this is a multifaceted problem, right? If you change the source of the material, if you change the electrolyte, you change the additive, you change the manufacturing, many things may not correlate, right? So fundamentally, they would like to say, what are actually at this interface are happening? What are the dominant process may influence? So they actually go out and select a few teams from the world coming from very different background. They call it focus group, where we are playing a very leading role, bringing people from battery, electrolyte, material interfaces, as well as DFT, computational scientists, as well as surface scientists, together to work on this problem for extended period of time, which led to, I think, our understanding of this oxygen activity or electronic structure controlled. Oxygen activity is key to dehydrogenate the carbonate electrolyte. So that's key, right? We realize we have DFT support, we have spectroscopy support. We say is happening on these electrodes. We can actually turn it on, turn it off, right? So this is really one side. So that's one component. Then separately, I was involved with this research called the development of lithium oxygen batteries, right? So essentially, we take out the transition metal out, we only have lithium oxygen, right? So instead of metal oxide, we don't have the metal, just lithium oxygen. That ultimately will give us much greater gravimetric energy density, potentially 3 times. So I was working on that for the past 10 years. And then the oxygen chemistry, extremely reactive, right? So you generate oxygen radicals in this aprotic electrolyte. So essentially, we worked with many different electrolytes. All the known electrolytes are not stable, right? Either aprotic electrolyte, polymer electrolyte, solid state are not stable. So then we, about 5-6 years ago, we approached our colleague Jeremiah Johnson. We said, let's work together, let's synthesize new molecules. Right, so he's with the organic background. Let's make new molecules so that we can design electrolyte solvent that can be stable against oxygen radicals. Knowing how the oxygen essentially react with facilitate dehydrogenation of electrolyte, we have new electrolyte solution that are more resistant to oxygen radicals, where oxygen radical react with solvent is also through dehydrogenation of essentially just take hydrogen away, right? It's really dehydrogenation. So we then, 3 of us, Julie and Jeremiah Johnson and my group, came together spontaneously to use the new solvent from lithium oxygen to test in lithium-ion batteries. So this was not sponsored per se by any intended program, but it's a result of long-term, stable, fundamental research where we can design, understand, and processes